very much. I hope you can hear me well online. Here, I'm sure it's fine. Yeah, so I'm Juliano NIETIEDT. I'm a research fellow at UWA, University of Western Australia. But as Luke mentioned, I come from Brazil originally. I'm a Brazilian, so it's in this presentation here, if you don't have a Brazilian accent, apparently you cannot speak. So luckily, yeah. All right, so I'm going to be talking about helical anchors, which is a topic that we've been working a lot at UWA. And some of you, if you attended the ISFAL conference, you see that there's a lot from what we presented there, but this is a summary of all the work me and some of the students presented. So this is just an outline of the presentation. Just initially, what is a helical anchor, our concepts, what we're studying, some centrifuge tests, and then some concluding remarks. So this is a helical anchor, which is a helix plate attached to a shaft, and this is installed by torque and axial force. It's pretty much like a screw. Everybody put a screw on the wall on a hardwood floor someday. So it's exactly the same, but in soil. And the shape can vary. You can have multiple helixes and different shapes. And we think this is a promising solution for the offshore because it's a silent and fast installation. So it's as easy as screwing a screw on the wall. It's similar offshore. It has a high axial capacity compared to its own weight, compared to a normal pile because of the plate, the bearing area. It has potentially lower manufacturing costs because it can be as easy as welding a plate to a shaft, and is also easy to decommission by reversing the rotation. It's important to mention that this is already common practice onshore. There's lots of applications from large piles to pile groups, rectifications of existing structures, anchors for retaining walls, and also some small offshore applications like this mussel farm in New Zealand. But the problem is that offshore, the loads are much higher. And also providing torque and axial force, it becomes a challenge. You don't have a physical structure to react against. It needs to be on the boat or installation rig. So therefore, there's several shortcomings in terms of the application offshore, such as the large installation torque and crown force. The helical anchors are not very good for lateral loads because they have a thin shaft compared to a standard pile. There's also no high installation rig available, just some prototypes like this one from Viarme, which was for very large piles. So the motor here is on top and is reacting against one of the biggest vessels they have, so it's likely to be expensive. And there's overall lack of confidence in the solution because of the limited use overall. So in partnership with GeoWind and University of Dundee, we've been working on helical anchors for the past 2 years, and we have a few concepts that I'm going to show now. The first one being the jetted helical anchors, which is a concept of injecting water during installation of the anchors to mitigate the large installation torque requirements and also the lack of installation rig available. So with lower torque required, you can likely use smaller rigs and smaller vessels to do the installation. We also have the concept of clustering those anchors in groups. So again, you can install smaller anchors, and because they are grouped together, you have an overall bigger capacity that can accommodate the large offshore loads. And this can also help a lot in terms of the lateral capacity, because again, you're going to have the group acting together with probably a frame on the soil that also has some lateral capacity. And this is work of one of our PhD students. And the third concept is the HEPLA, which stands for helically embedded plate anchor. So the concept is you install this helical anchor as if it was a normal anchor, but then you retrieve the shaft and leave a cable on the soil, like a mooring line. And these can potentially, two things, lower the installation torque because the shaft can be much smaller. is not required for the sustain the lateral load. And also increase significantly the lateral capacity, because then the plate can rotate, and you also have the mooring line through the soil that also helps with the resisting the loads. So this is the work of Viarme, another PhD student. So let's talk about the jetted first. So this is the centrifuge setup. So you can see we have a torque and axial load cell at the top, which is connected to a fluid rotary union. So here's where the fluid is pumped in through these injection holes. And at the bottom, we have it connected to the screw pile or the screw anchor. So here in the detail, you see there are rollers above and below. So this chamber doesn't rotate. It's free to rotate actually against compared to the helical anchor. So you see a video of this working. So the fluid is injected in this chamber, and it flows through those over holes, which are connected to a hollow shaft. And then the jets, they come around the helix. And we had several different jets configurations, starting from just jetting at the top and at the conical tip, and then top and below the helix, just through the cone. And we also tried some large anchors as well to see how this works, and everything compared to non-jetted helical anchors or standard installation ones. So here I have a video of this working. So we do everything in flight. So we start the installation without jetting to avoid scouring the soil at the surface. Then we turn on the pump, and just by assigning a constant weight to the system, the anchor goes in by its own weight. Once we reach the target depth, we wait a little bit to dissipate some pore pressures generated, and then we conduct the pull out. And then you see the anchor coming out. Yeah. So that's the process. And then we started looking at results. So it's worth mentioning that this was just a proof of concept of an idea that we had. So it's at its early stages. We're going to keep on studying this solution. So here I'm plotting the model torque with installation depth, and those two black curves are non-jetted standard helical anchors. The only difference between the two lines are the constant weight that we assign to the model. And you can see that there's no big differences in terms of torque. And then we started doing several different jetted installations, varying the flow rate from 0.5 milliliters per second, 1, and then 2. And what we saw is actually a very significant decrease in the torque, up to the point that we saw a steady state torque with depth, meaning that the torque was not increasing anymore with penetration, which was quite interesting. Then again, compared to the standard helical anchor installation, we started changing the configuration of the jets. What we saw is that jetting just through the conical tip doesn't help much. But then if you jet from the tip and above the helix, you have a good decrease in torque. And the best one being when you're jetting around the helix above and below, which is where most of the torque is coming from. Then when we put everything together in terms of a torque reduction, comparing the torque to the reference helical anchor, we saw an overall up to 70% reduction in torque compared to the standard helical anchor, and even for those relatively small flow rates that we applied. So what we think is that the pore pressure that we generate during installation is just around the helix, and it's not big enough to actually fluidize the whole soil and affect the whole anchor, all the soil around the anchor. And then people, first thing they ask is, of course, is the torque, what about the capacity? And then we saw that a 40% reduction in capacity if you install to the same depth. But then when we look at the capacity to torque ratio, or how much capacity you get for a specific torque, we saw that by jetting, increasing the flow rate, we saw about 2 times more capacity for the same unit of torque. So we know jetting reduces the torque. which means that for a given rig that you have in the field that has a torque capacity, you can go deeper with the same anchor. And what happens to the capacity in this scenario? So let's look at that steady state torque that I talked before. We did non-jetted installations trying to get to the same, to this target 10 kilonewton meter in prototype scale. The anchor went 1.6 D in the soil. And this is how much capacity we've got. But then when we did the jetted installation, we were able to install up to 6D, and this is the capacity that we've got for the same torque. So it's 13 times more capacity. And then if we put some numbers there, extrapolate a little bit the results, we can see that for we got 3.6 tons per kilonewton meter in terms of capacity to torque ratio. And then if you think that we can have a rig in the field that is able to produce 500 kilonewton meter torque, this would be a 18 meganewton anchor, which is not bad. It's actually quite good. A few anchors of that should be able to resist the loads of one line of a floating wind turbine. And I have to mention that the anchors could have gone deeper with the same torque. We had to stop, not because the torque started to increase, but because the model, we didn't expect the model was going to work so well the first time. And there were some physical limitations on lengths and other things. So now let's talk about groups. So we conducted a bunch of group tests with varying the relative distances between the anchors, and we did in clay and sand. So here I'm going to show a video of the procedure in clay. So we conducted installation of one anchor, and then we installed the second anchor very close and varying distances. And then we conducted the pull out of those anchors together to see if there was interactions and how can we calculate that? Does it agree with what we know about soil mechanics already? And as a matter of fact, it does. We didn't see interaction for normally consolidated or over consolidated clays spaced at least 1.5D away from each other, which is what we expected from simple calculations in clay, which is quite reassuring for the solution. So it brings, okay, we know how to calculate those things. Helical anchor is not a special thing in regards to group effect in clay. And then we did the same thing in sand, but here it was a bit more complicated because we didn't want to ramp down in between installations to not lose all the residual stresses and that build up during installation of those anchors. So we developed a whole installation tool that can do multiple installations in flight and also extraction of the model. So we start by pre-embedding the anchors a little bit at 1G, just so the shaft don't move a lot during spin up. And then we go with the tool and this bayonet sort of connection. And then we conduct the installation of those anchors. Then we go to the loading point in the mat, and then we do the extraction of the anchors. Everything while looking at displacement through a 6D marker, which is there's a camera that reads this marker and can give you 6 degrees of freedom in terms of movements. And then after the first extraction, we thought, why not keep on installing these anchors, going to deeper depths and conducting more pullouts? So we just kept on doing that a few times. So we got actually more results per test, which we can explain later in terms of if there was any impact of doing further installations or not. And then again, the results were very reassuring in terms of they were consistent and we saw substantial interactions with the anchors clustered close together. Of course, it depends on how deep you were and it depends on the density of the soil, but overall we could match those with simple numerical plate anchor calculations, which is consistent with our expectation and again reassuring for the application of this in practice. And then our final concept is the HEPLA, helically embedded plate anchor. So here's the the process for a vertical extraction. So we start installing the anchor to the target depth. Then we retrieve the shaft, everything in flight again. We recentered the line with the center of the plate. And then we conduct the extraction of the anchor, which you should be able to see in a little bit. There it is. Yeah. So that tip bit with the blade is what is providing the resistance. If you look at some results here, I have in black conventional helical anchors results, and in red these Hepla capacities, vertical pull out in sand. And what we can see is that there is a consistent behavior between the two solutions. The only main difference is the stiffness, because one is loaded through a mooring line, which is much softer than the shaft. But this is not likely to be a limitation. It's just the capacity of the plate seems to be consistent between the two. And then we did the same in clays, but in clays we also did, excuse me, lateral pullout. So here the installation, you see that it's exactly the same. First install to the target depth, then retrieve the shaft. And once the shaft is above the soil, we use a secondary actuator attached to the mooring line. So you see the line cutting through the soil in the process of laterally loading this anchor. And then you can see the line disappearing here. And when we look at results, again, we see for vertical pullout, which is the comparison between those two lines, the Hepla is the black line and the yellow is the conventional helical anchor. We see similar capacities, but a softer behavior for the Hepla. But the main benefit is the blue line, which is the lateral load. And then you can see that you can actually mobilize more capacity because you have the full plate aligning with the direction of load, plus whatever the cable can give you through the soil in a reverse catenary type of mechanism. And so for this test, we pull the anchor up to this point, a little bit beyond the peak capacity, and then we cut the soil. We stopped the centrifuge, of course, cut the soil, and then we saw the anchor actually moved up and rotated a little bit to align with the mooring line or the cable that we saw in the soil. So then again, really interesting, and was good to see that the anchor actually moves and realigns, exposing the full bearing area to the direction of the load. And of course, we think about using this solution together with the jetting, because jetting probably impacts the soil on a vertical direction. And then if you load on a different plane, you're probably mobilizing virgin soil, which might be mitigate a little bit of the capacity lost. So concluding remarks, so jetting enables larger anchors to the target depth. Or the same anchor, you can go deeper, which significantly increases the capacity. The groups, they behave broadly as expected in both clay and sand, which is reassuring for design. And the Hepla concept was proven, and it showed similar behavior to conventional helical anchors, but now we also have a significant lateral capacity and incline capacity. So the idea is that we can merge those ideas together and hopefully have a very efficient solution for the floating facilities. And thank you very much for your attention. And this is the group that worked with